Okay, so parallel pressure parallel to the magnetic to some magnetic field line causes an instability, and it's true of fluid motion. It's true of water shooting through a hose. If you have water if you have water shooting through a hose, and it goes around the bend, there's centrifugal force, and it pushes it out further. Um,
Can you send it again?
Water is shooting through a hose,
Okay.
and
What about centrifugal force? What
if
did you
it's
say?
shooting around the bend, there's centrifugal force that pushes the hose out. In
Okay.
other words, if I were holding it here, I'd be pulling in this direction so that the water could shoot around.
Right.
And that means if I let go, the hose would accelerate in this direction. And that's why when you put gas in the car, the hose shakes sometimes.
Like when you hold the water hose
The tube.
from
Yeah.
one end, you see the other one
Crazy,
like crazy.
yeah.
Yeah, yeah. It's like that. Okay, so that's actually a mechanism for shock waves. If they're parallel, if if the shock front is moving in this direction and it's parallel to the magnetic field lines, uh, then I can have an excess parallel pressure here. And it doesn't matter. It doesn't matter that if it's going in both directions. If the water were going in both directions through the hose, it would also be unstable. In fact, instead of it shaking around, you get a standing mode. It would just wiggle more and more, but the head wouldn't have to move. Um, and um, that's actually a way to solve Feynman's problem. He said, what if you had an anti-garden hose where you suck water in from a tank along with.
What hose?
What is the question? I'm not familiar with this.
Feynman, in his autobiography, said he once asked people at Princeton when he was a graduate student what happens if instead of shooting water out two ends of a garden hose to start it spinning, suppose it sucked water in,
Okay.
and he actually claims to have done the experiment where he hooked a garden hose up to a vacuum pump and then put the whole apparatus inside a tank of water and turned on the vacuum pump so it would suck water in through the. He wanted to see which direction it spun. And he asked everybody what direction they thought it would spin in. And of course, he got lots of different answers. And when he did the experiment, he said he got a definite result, but he's not telling anybody.
Why?
Because he wants people to be curious. Uh, so the point is, you can get magnetic turbulence, and that's a perfectly good way to make a shock, because once you have magnetic turbulence, it scatters the particles. Uh, Now, did you ever find the most recent file and give it
This
to
one
us?
I didn't quite last time.
What about the other one?
Other one I didn't find yet.
You didn't find it. Alright. particles colliding with the particle colliding with the wall goes from speed v to 2v plus u. This is a non-relativistic particle bouncing off a wall. The wall is moving at velocity. The wall is moving at velocity u. So the speed goes from v to 2u, and v squared goes from v squared to 2v to v squared plus 4uv plus u squared. But let's assume that v is greater. Let's assume that v is much greater than u. So delta E over E. The energy is 8 times u over v.
No, without the E. Unified.
Right. So for homework, do it for a relativistic particle. That'll be one homework problem. Okay, is it 8 times u over v? Because it's v squared goes v squared goes to v plus 2u squared, v squared plus 4u v equal v squared plus
Wall is moving.
Yeah, with the velocity u.
plus alright, let's write it this way. V squared we'll write as 1 plus 4u over v. So actually the change in energy is 4u over v. Okay. Now Fermi's cosmic rays have a power law, beautiful power law in the energy spectrum, and for many years it was a mystery why they have a power law like that. It was assumed to be an important clue to the origin of cosmic rays. And there are actually two deep questions that nobody could answer. One is, why should there be cosmic rays at all? And the other is, why should they have this beautiful e to the minus 2.7 power law spectrum?
What is the definition of cosmic ray?
Relativistic particles in the galaxy. And actually they're extragalactic too, because you see the radio spectra from the electrons in extragalactic sources too, and have the same power law spectrum. Okay, so Fermi's argument was, okay, suppose the change in energy is a fixed percentage of the energy, which you would get in such a collision. If suppose V is C, relativistic, then U is the same for all the cosmic rays, and therefore U over C is always the same. And this is actually an alpha. Um, and this uh, this is actually I call delta y here. In the notes you didn't type it. All right, and let's say that the probability of escape is uh, well, delta n if they escape is negative, so the probability of escape is delta n over n. Let's say in any for every energy gain, there's a probability that you'll lose. Like, you bet, you go to Las Vegas and you bet all your money on the red at the roulette wheel, and so if you win, you almost double your money, and if you lose all of it. Um, but this is, let's say for each play of the wheel, there's probability of gaining and probability of losing. The gain is the fraction of energy of your original energy that you gain, and the loss is the fraction of the players or particles that get lost in that turn. Now, obviously, delta log n over delta log e is
Why is this a constant?
why is what a constant?
The probability of escape.
Good question. In Fermi's original idea, he was unable to show that it was constant. There's no reason that the escape rate from the galaxy should be constant, or no reason it should always be in proportion to the energy gained. And that's why Fermi's idea was dead in the water for about 25 years. Anyway, you can show, if it were true, I mean, it's true, in Las Vegas, it's true in the stock market. The more stock you buy, the more you can lose and the more you can gain. But it's always proportional to how much you bought, how many shares you bought. And by the way, the distribution of wealth in the United States is a power law. It's actually very close to e to the minus 2. Wealth to the minus 2 power, which means that in all logarithmic intervals of wealth, there's the same amount of wealth.
Even now?
Yeah. So Bill Gates is, the richest guy in the country now. He's, worth of $100 billion, which is
Nothing compared to us.
what?
Which is nothing compared to us.
Well, if you count all of us together,
Still.
like everybody except Bill Gates, then it's a small fraction. But it's only 1 over a log factor. Let's say you're going from 100 billion to I don't know, 100. So it's 9 orders of magnitude. So it's about a log of 20. So multiply 100 billion by 20, and you get a couple of trillion, which is it's probably a little bit less. It's probably somewhat less than the total amount of than the total money supply in the U.S. But if you count Warren Buffett and you count people within 1/e of Bill Gates, there are probably a few more. So it's a few hundred billion, and then you multiply it by 20 or 25, you get 10 trillion.
And 1% of the population has about 90% wealth in the top 1%.
Yeah, but the top 1% is spans many decades in wealth.
Yeah.
Because you only, if it's e to the minus 2, you only have to go like from $100 to $10,000, which is still poor. I mean, let's say you go you say you count everybody who has over $100,000 in the bank, in the top 1%, and or anyway, that's 300,000 to get from whatever your definition of the top 1% is, to get from 3,000, 300,000 to 100 billion is more logarithmic intervals than to get from the most poor to the top 1%. So that's why they have 90% of the wealth, because it's an e to the minus 2 parallel. And it's because when the alpha loss equals alpha gain, then the number greater than e goes as e to the minus 1, which means that dNDE, which is the number per unit wealth, it goes as n to the e to the minus 2. But the number per unit logarithmic wealth, which is really, you really want to dn d log e. I wrote it here. It's minus alpha loss, and so when this is equal to minus 1, it means you have equal amounts of energy in each logarithmic interval, because the energy is equal to E times n. I mean, that's the energy in particles with energy E. And let's call this W. So dW d log E is equal to minus alpha loss over alpha gain plus 1. So if this is minus 1, plus 1 makes it 0, which means W is constant in log E. So you can do it this way too.
Why did people go back to this theory?
Why did what?
People go back to this theory to say that it's constant. What made people think that it's constant?
What made people think that what's constant?
Alpha loss.
Right.
I mean, you said that Fermi didn't show it. So
The loss rate.
wow.
Fermi didn't show it. And therefore his theory was not. It was the only one around. It was the only game in town, to use gambling terminology. But nobody really believed it. Nobody was satisfied with it,
And now?
except for people who were. Now you just wait patiently. She doesn't even know how to spell geometry. Okay. Now, at a shock wave, it is constant. Because, well, we'll see why. because the gain, first of all, there's always gain. If you each time you cross the shock, there's a gain, a percentage energy gain, and it's just the difference in the upstream and downstream shock velocities divided by v. But when v is equal to c, well, never mind. It's divided by e. The rate of loss. Yep. The rate of loss, as we'll see, is just u plus over v times a factor of order unity. Because they're lost by convection. If you have an infinite plane and particles make a random walk, they always cross the plane. They never escape the plane. If the particle made by chance, 20 consecutive moves to the right without going to so it's far from the wall. But since it gets to go on forever, it will always, at some point, recross the wall in the other direction.
What is the direction of the wall?
Direction of the wall is, that's the wall.
No, I mean, where does it go?
I don't understand. Where does what
the
go?
The particles, how do they
They go to the left and to the right.
Within the frame of the wall.
The point is, if it's equally likely to go to the left or the right, it never escapes the wall. And the number of particles escaping, therefore, per unit time, is just due to the convection of particles behind the wall. And the rate of convection is proportional to the fluid velocity.
But if they accelerate, do they escape it eventually?
Eventually, but for now we're assuming it's an infinite plane. And what that means, to put it differently, we're assuming that the most likely mode of escape is convection, as opposed to just becoming very energetic and escaping any which way they want by brute force. So that'll mean that the spectrum will somehow depend on u minus minus u plus divided by u plus. This here is not clear. What I really should write is n great. The number of particles that make it to be greater than e is proportional to e to the minus minus u plus over u plus and then times some fudge factor. And now if u minus is equal to 4u plus, which is the case in strong non-relativistic shocks, then this is e to the minus 3 u plus over u plus times fudge factor, and
What's the order of the fudge factor?
what?
Is it of order of 1?
Yes, it's of order 1. Fudge factors are always of order 1. Anyway, that's the general idea. So now we're going to derive it formally. Now,
No. You do it.
start with Boltzmann equation that describes the scattering. Let this L here denotes the lab coordinates, and without the L, well, we can put the L in here. This C denotes a collision operator. Now I'm going to assume that the collision operator is going to eliminate the anisotropic component. Let's say that F in brackets is the isotropic component.
This is what S was supposed to be.
What?
This is what the small S was supposed to be.
The small what?
The small S.
Small s?
Yeah, in the bracket and the derivative.
Yeah, I guess so. But this F is in the fluid frame, and this averaging is in the fluid frame. By definition, I mean, if there's no more scattering, if the scattering has totally equilibrated the particles, by definition, this is zero. But by definition, it's in the fluid frame. Because the fluid is isotropic in the fluids frame. And as we said, viscosity is nothing other than isotropization by collisions. So this is actually what give us viscosity, but it'll give us a lot of other things too, and that's what's interesting. Okay, now convert from lab to fluid coordinates.
What is tau?
Tau is the collision time. And they don't have to be binary collisions. In fact, they may not be binary collisions. They have to be collisions that preserve the particle energy in the frame of the scattering center. Okay.
Maybe you should change the. You have this term. Maybe you should change this x to be something else.
Change what? This what? It's a C, not an S.
The x right here. It looks like this. And then this x. It looks like a distance.
No, actually, in my notes, it's time. She just wrote. Okay, so this unfortunately is in the lab. The F is measured by the lab observer, but this F is measured in the frame of the fluid. So the idea is to convert the left-hand side to fluid frame coordinates, fluid frame quantities. So what we want to do is expand F of uv and this is a V here. We want to expand, and this is the pitch angle. This is U is equal to Vx over V, which is cosine theta. Okay, if we expand it in terms of spherical harmonics, where this is first John's polynomial, and then F2 would be second the L equal 2 spherical harmonic and so forth. And then we use perturbation theory to solve perturbatively for F1 and F2. And then if we take the angle average of this equation, we'll get an equation for F0 of just V and X with no mu dependence. Now this is three spatial variables technically and one velocity variable. This is the magnitude of V. And by ignoring where it was pointing, which direction it was pointing, we've eliminated 2 dimensions. So we went from 6-dimensional phase space to 4-dimensional space. And so now let's assume that
Aren't we talking about 1D here?
no, the velocities can be in 3 dimensions. The spatial dependence is only 1D, but the analysis is good even if it's more than 1D. I'm going to write, for gradients, I'm going to write d dx for simplicity, but it would be valid, the method is valid in 3 spatial dimensions, even if it's not isotropic. Okay, so assume now that the assume that the scattering isotropizes particles in some frame given by u of x, not v of x, which may or may not be the center of mass frame of the fluid. In other words, conceivably the magnetic scattering extensions can have some finite phase velocity moving through the fluid, but mostly people assume that it doesn't. Assume a parallel shock so that it's moving. Assume a parallel shock, which is moving in the x direction, and we'll take the angle mu to be relative to the x direction. Okay, in the lab frame we have these 3 variables. This is an L. Okay, now this was the Boltzmann equation that we had just before. We replaced this VLX with VL times cosine theta. And then this is the collision operator. And right now I'm using a small f to denote phase space. So this is the phase space density, and it's a function of 6 dimensions. Now, for a collision operator, I could have been fancy. I could have just used 1 over tau. But instead I'll be fancy just so introduce you to the concept of pitch angle diffusion. This is the diffusion equation on a sphere, where particles are maintaining their velocity because the magnetic field doesn't change their kinetic energy, but it only changes their direction. So it's basically their directions are diffusing on a sphere, and the Laplacian this is the Laplacian basically on the sphere. Okay, we write F as an isotropic component plus F1 mu plus F2 mu. This is second spherical harmonic. L equals 2 spherical harmonic. And we assume the distribution is close to being isotropic, so that F1 is and F2 and all higher order terms are much less than F0. It's a crucial assumption. Now, when we say it's close to being isotropic, the deviations from isotropy will make a viscosity, but we're treating it perturbatively. Okay. So now this here is the collision operator, and I'm differentiating F with respect to mu, which means F naught is going away. I'm left with an F1 times the d mu nu. And then I multiply by 1 minus mu squared and differentiate it. So I get mu minus mu cubed. No, sorry. df1 df d mu made this mu go away. So assume d mu mu is constant. So then it's just d mu times 1 minus mu squared, which is minus 2 mu. So this term, when plugged into here, became this. And then let's see what happens when I differentiate this with respect to mu. I got 2 mu, which means I got 2 mu minus 2 mu cubed here. When I differentiated that, what happened? Just a second. I should get 2. It's good. Well, alright, let's all believe Justin.
No, that's because you have 2 mu becomes 2. So if you take a 6 outside, you have
Right. 2 mu cubed, d mu of 2 mu cubed is 6 mu squared. And then I had just 2 mu, and that's the same as when I differentiate with respect to mu, I get a 2, and that's the same as 6 minus 1/3. Okay. How come the mu squared minus 3, mu squared minus 1/3 remain the same? Because when Legendre made his polynomials, he made them eigenfunctions of diffusion on a sphere. And if the scattering had been large, I would have used this, and I would have gotten basically the same results. I would, instead of getting d mu mu, I would have gotten 1 over tau.
How do you calculate that?
Well, I can use quasi-linear theory to calculate the scattering of rate of particles on alpha anyways. But you need to know the level of turbulence. I have no idea what this is all about. Now, in steady state, let's go back to this equation. In steady state, we want to set this partial t equal to 0. And that leaves just this term on the left-hand side. So that's VL times UL times F of L. And this, we still have this collision term. But remember, this collision term was simple in the fluid frame. I mean, we just did it. But so now we want to go to work on the left-hand side. We want to convert this to fluid coordinates. Okay, so first of all, we remember that phase space density is a Galilean invariant, which means the phase space density is the same because dx and dv for Galilean transformations are invariant. So the volume element of phase space is invariant, and therefore F is invariant. So the total number of particles being the phase space is invariant. Alright. Now, V of x is equal to V mu. This is fluid coordinates. And it's equal to VL U of L minus U of x, because if particles were moving exactly U of x, then in the fluid frame it has no velocity, right?
Okay.
If the fluid is moving at velocity 17 and the particle's moving at exactly the same velocity, then in the frame of the fluid it has 0 velocity. So just the lab velocity minus the x component of the lab velocity minus the fluid velocity, which is assumed to be just in the x direction. If I were in 3 dimensions, then this would just be a vector. And this would be this equation would be a vector equation with 3 separate components. Okay, v perp squared is the same as it is in the lab, because there's nothing to transform perpendicular velocities, and therefore I can rewrite this as follows. V perp squared is v squared times 1 minus mu squared. Okay, what?
No, I just said you should write L of the V square perpendicular. And also perpendicular on the other side.
Okay, an L here, yeah.
Yeah, perpendicular on the V on the other side of the equation.
No. I mean, this should be an L, I agree. But v squared is the total velocity, and the 1 minus mu squared take. Okay, I have no idea what this is. Typing error. What?
Maybe she fell asleep on the keyboard. She fell asleep on the keyboard.
Yeah.
Just
Okay.
like few seconds.
Now here comes the part I don't like. Alright, F is the same as FL, so the first stage is fairly simple. But now, when you transform coordinate systems, here, this is the part where people always say, okay, we'll just take the Jacobian. But I never liked Jacobians, and I just rather think in terms of what's going on here. So, how do I keep mu L and VL constant to take a purely spatial derivative? The problem is when I move to a new place, when I move from x to x plus dx, the velocity may have changed. So even if in the lab nothing changed, mu is the same and v is the same in the lab, in the fluid velocity, in the fluid frame of reference, the velocity of the particle can change, even though it never scattered, even though it's exactly the same in the inertial frame. So I have to take into account the fact that constant mu and v in the lab. In other words, the particles obeying Newton's first law. Nevertheless, because my definition of mu change was spatially dependent, I have to take into account the fact that mu changed with x even though mu L didn't, and that v changed with x even though VL didn't. Okay. Now, you want to use these equations to substitute in for d mu dx and dv dx. I mean, these are obviously equations that relate the lab coordinates to the fluid coordinates. So dv dx for a particle moving at constant velocity in the inertial frame, it's just minus mu times d mu dx. And you have to think about that. It's because du dx is basically the change. Du dx times dx, which is du, is the change in the fluid velocity. Now, if that change is perpendicular to the fluid's original velocity, then it's like adding a perpendicular component. It's the lowest order. You haven't changed the length. And obviously the change in length is proportional to the cosine theta. If cosine theta is 1, then it's added in the same direction. So the change in v is just du dx times mu. And actually there's a minus sign, because if u increased, then, well, it was minus u. So just do it. You can do it with using algebra. dv dx is equal to, no, dv, if u increased in the x direction, let's say mu is 1, then the particle velocity in the fluid frame decreased by the same amount, so therefore there's a minus sign. And what about d mu dx? Well, let's say that this is the velocity v. And this is d mu. Sorry, this is du. So we don't have to worry about the denominator dx. We just want to show that the change in mu, which is the change in the cosine of the angle, is proportional to 1 minus u squared du dx over v. Let's see if we can do it from here. We have an expression for d mu dx. It looks like d mu dx is... See, I can't use this equation because it's multiplied by v, and v is not holding still. So how do I do it? If I differentiate this equation with respect to x, well, I'll have to differentiate v with respect to x and mu with respect to x. So I might as well just do this. I prefer using a picture. This is theta. Okay, obviously it's proportional to du dx. I mean, u changed, and the transverse. Okay, if the transverse velocity obviously did not change, and cosine theta went from being this divided by this. No, cosine theta is Vx divided by V. And then it went to be V plus du. No, Vx plus du over Vx squared plus 2Vx du plus plus V perpendicular squared. Okay, V perpendicular squared Anybody see how to derive this? It's obviously proportional to well, I know how to do it. I just define mu. Mu is equal to Vx over V. Mu plus d mu is equal to V of x plus du, where u is the velocity, over no yeah V of x plus du squared plus v perpendicular squared to the 1/2 power. And this is equal to Vx times So it looks like it's equal to du over v. No, it's not quite right. Yeah, if I subtract this from this, I'll get d mu. And it's basically this term minus this term to lowest order in d mu. And obviously this has a mu, a d mu over v in it. But there's another term. It comes from taking Vx here I simply subtracted the numerators and left the denominator in both cases was just v because I neglected the u in the denominator. But now I have to take Vx times 1 over Vx squared plus V perp squared minus 1 over Vx plus du squared plus V perp squared okay, and this will have a term that's proportional to du. Right? To first order in du, if I take this difference to first order in du, then I'll get this. The first term just gave me du dx over v, but the second term will give me a u squared du dx over v.
So this means the VL is constant and
VL and mu L are both constant.
both are constant?
Yeah, it's just the change in frame of reference.
Okay, so VL is constant.
This is a Schwarzschild-Christoffel term. It's due simply to the changes in my coordinate system.
Yeah.
In reality, the physical velocity is not changing.
I think it's better doing in angular wave. This is theta. Then d theta is sine theta d theta. That's like d mu. Should be sine squares plus I don't know.
Yeah, yeah.
We have to check some. I understand
No,
one side that is
this is just a trigonometric
yeah.
derivative. This is d mu dx is d cosine theta dx. Uh, and you know, u is like the x coordinate here. I could just say d mu du and forget about the dx's, and it's like saying d cosine theta. Um,
dx
well,
d
it's like saying d cosine theta is equal to
the change in ux the change in vx is
uh,
du dx, no?
it's equal to dx over x squared plus y squared. Okay. Uh,
Square
with y held constant.
with the square over
Right.
root.
Yeah. So this is equal to 1 over plus x over x squared plus y squared.
That's okay. If I simply draw a line from perpendicular joining this line, perpendicular this line,
Yeah.
then you get this v d theta with the small angle between these two lines
Yeah.
is du sine theta.
Du
sine theta.
sine theta. Well,
I mean this angle is theta between x direction and v.
1 minus mu squared. It could be that is this possibly should be to the 1/2.
Then you get sine squared. That's 1 minus mu squared.
Is there a 1/2 here?
No.
Because 1 minus mu squared to the 1/2
No.
over v is
You get 2 sine theta here. V is d theta is du sine
yeah.
theta, and this d theta is d mu over sine theta.
Yeah.
See, this sine theta comes here, so this is sine squared theta.
Sine squared theta. Okay, so that's what this is.
Yes.
It's sine squared theta. And finally we get okay, remember I had this df dx and I have these two terms. And so the left hand side of the equation just becomes this. This is Vx, this is df dx, this is the acceleration parallel to this is the imaginary acceleration due to the change in the inertial frames times df dv. In other words, mu times du dx is the acceleration in the x direction of the fluid frame, and this is the no, I'm sorry, this is the acceleration in the direction of v due to the inertial imaginary forces. And this is the acceleration perpendicular to v, which is why it depends on df d mu. And it's just sine squared over v, which is what we had up here.
Can I ask a question?
Yeah?
Vx is constant in x?
Yes.
Yeah.
Vx lab is constant.
So you you can get this equation straight from this, using this.
Using what?
Using this equation
This equation?
and say that dvx dx is equal to 0, you get this equation right away.
I'm not following. Which is this equation?
Using this
This
equation,
top equation,
yeah,
yes.
and saying that dvx, which is this one, dx.
No, this is dvx lab.
So saying that dvx
Lab.
dx equals 0 gives you the middle of this one right away.
Where do you see dvx lab here?
Yeah.
If this is constant,
Yeah.
then dv dx is equal to this, but I still don't know what d mu dx is. Oh, that's what I'm trying to find. It's equal to d minus d mu dx divided by v. Oh, you're right. Thank you, Yossi. Thank you. Did you all catch that? If you take this and you add and you combine it with dvxl dx equals 0, well, let's get rid of all this. I don't want it. Oh, and this is a square here, isn't it? Yeah. Right. It immediately gives you this. Beautiful. Thank you. Anyway, we finally get this equation, which is what we wanted. We have everything now in the fluid frame, but it's still a six-dimensional phase space. And we want to reduce down to 4 dimensions. We want to make V, we want to have something that depends just on the magnitude of V. Okay, so what we do is we take this and we average it over mu. Let's take the isotropic component. And we just remember what the average over a sphere of mu is, of various powers of mu. Odd powers average to 0, and even powers average to 1, 1/3, and 1/5. Okay, so now I do believe this should be F naught. Okay, so what did we have here? Well, mu to the first power, when we averaged over that, we got 0. U times df dx, well, that survives. No, wait a minute, wait. Okay, no, I get it. What we need to do is we need to substitute for f. Alright. So this term, if I put in f0 into here, then the angle average chooses the u, because everything's isotropic. So where did that term show up here? That was this term. U times df0 dx was the very first term. If I put in f1 into here, f1 mu, then I get v u mu squared f df1 dx. But the average of mu squared is 1/3. So here we go. 1/3 v times df1 dx. That's this term. So far I have these two terms. And there's just one more thing. If f2 squared, if I put the f2 into here, I'm going to have mu squared times u. Yeah, and so there actually should be a mu here.
You know that all of them are off.
What?
I don't know.
Okay, the rest of these things are proportional to du dx. I think I did all these. I think I did everything proportional to df dx, and the other ones are going to be proportional to the u dx times df dv. All right, so I'm gonna have a df d0 dv, because this mu times this mu will begin the u squared. So I should have v mu squared df0 dv, and that'll be a 1/3 coefficient. So that's this. The u dx times v over 3 df0 dv was the first term. And then what else? Alright, if I put in a 1 in here, then I'm going to get mu squared here, and that'll be times u. So it'll be u df1 dv divided by 3. So that's this term. That came from putting the f1 into here. And if I put in f2 into here, I get u cubed times vf2
Minus mu over 3.
so there are two terms involving f2 df2 dv times v.
So basically
But they came from putting the f2 in here and then keeping this term. if I put F2 in here, I have I powers of mu here, so it picks out the V mu term here. So it's going to be V times df2 dv times du dx times some numerical coefficient. And there were two terms. One was u squared and the other was 1/3. So the mu squared is going to give me mu to the fourth. This be mu cubed times this v mu is mu to the fourth, and then I'll get a 1/5. And the 1/9 came from this being 1/3 times this 1/3. And then I have to deal with these terms here, which is going to be another major pain. I think it's going to pick out. Oh, you really have to go through it. But they're going to give me two more terms here in F1 and F2. And we can write the collision operator.
Why is it equal 0?
Is it equal to 0?
No, it's equal to.
It's equal to
df
right, df1.
Why df1?
No. Well, alright, never mind. We'll write df dt collision. It turns out I'm only going to keep the f1 term. Unless I really want to. Okay, so we got one more.
Wait, but why choose df1?
Where?
Where
Well, I didn't. I suppose I could add. I don't have to put the 1 here. No, here I have to put the 1. And here I think I also have to put the 1 because I derived it. Up here, didn't I, somewhere? It was f minus f0, so it certainly leaves only f1 as a leading term. And so I'll write I'll just write f1 plus all the other stuff. Okay, now I'm going to assume that the scattering time is much less than the other time scales. Like the time scale for the change in velocity to make the distribution anisotropic. And unfortunately, that assumption makes this treatment inapplicable for certain situations, like for velocities that are very close to thermal, and also for relativistic shocks. This formalism, unfortunately, is invalid. But what that allows us to do is to assume the distribution is almost isotropic, which means that that all these higher order terms are small compared to f0. In other words, the distribution function is nearly isotropic.
Why is it not valid in one side isotropic? I mean, you can take more terms.
What?
No,
Oh, but it becomes, it doesn't converge. How do I keep
but you can always decompose any function in the
into an infinite number of terms?
yes.
But that's an infinite amount of work unless it converges rapidly.
But if you have in principle infinite number of terms, then it's valid, isn't it?
Yes, yes. Alright, this is in terms of f naught. I'm not sure I'm not sure I need any of this. Oh, I see. Yeah. Okay, here's the point. The point is I got I had an equation here that related f1 and f2 to f naught. Sort of. Um, I see it's almost 4 o'clock. Let's just say what we're going to do. Now we want to equate terms of comparable order. So terms that of order f naught, did we have any terms that were of order f naught? Well, we had the f naught dx.
How do you know that this is one? Then df1 dx.
I don't. Wait a minute. Wait. This is one. Let's say this has an f naught here, and this has an f naught here. So I'll keep these two terms, and maybe some of these terms are much smaller. But by the way, I see this as a bracket. Yeah, and this is the closed bracket. Look, I'm keeping all the terms in f naught. Let's see what else I have to keep. This is df naught dx times u. This is df1 dx times v. But what if v is much bigger than u?
And what if df1 dx is larger than df0 dx? We know that v0 is much bigger than f1, but does the derivative also big?
They're using different numbers. But you take derivative
think this was taken totally out of order. Okay, I think the next thing to do is to go back to this equation. We took the angle average, but but again, since we're equating all powers of mu individually, we can go back to this equation and equate terms that are proportional to the first power of mu. That's also valid. And man, I don't even know what equation 11. Here, look. It says substitute equation 13. Okay, now where did equation 13 come from? It came from taking the mu, the terms in this equation are proportional to mu. Sorry, the terms in this equation are proportional to mu. Like mu u times df1 dx is proportional to mu, and does that obviously give you this? If it's not really quick, I'm going to save it till next time.
Yeah, it makes sense because if
You
they're perpendicular to each other. Yeah. I think what you said it does what is it?
yeah, I think this is the point that f1 is related to df naught dx, df, and this is, I mean, this is intuitive to me. I can't even remember formally where it comes from. It's just that if a train slows down, people start to get accelerated, and that creates an anisotropy in the velocity distribution because those going backwards end up going backwards faster, and those going forward end up going. So it just creates an F1. So F1 is just proportional to du dx. Um, and anyway, the idea is to take F1, write it in terms of F naught, and then substitute it back into here. So that the terms in here that involve F1 will actually be written in terms of F naught. So I'm going to get a whole grand equation in terms of F naught. It'll obviously have these two terms in it, but it will also have this term once I write F naught in terms of, once I write F1 in terms of F naught, and I think it'll have this one too. And of course it'll have a collision term. No, it won't have a collision term because it's only going to involve F naught, and the collision term doesn't operate on F naught. So where did this collision term come in? It comes in when I evaluate F1 in terms of F naught, because this term will have F1s in them, and the lowest order on the right hand side will be F1, and it'll be proportional to mu, so I have to equate it with all terms proportional to mu to the first power on the left hand side. And It'll probably be the ones involving F naught that are the largest.
You don't have any on that. You don't have any in this equation. You already did
No, no, sorry, I mean this equation,
okay.
which also has this. Alright, get out of here. I'll see you tomorrow. Now, there's a, since my wife is in the hospital, oh, I hope I didn't just erase that.
You have to stop recording. I think file was saved. No, no, click small bar. Maybe, maybe, yeah.